Good afternoon. Today, I would like to continue our class in electric physics. Today, we will start or we will discuss about the electromagnetic induction and inductance. So, in previous chapter, we have discussed about the capacitor and also a resistor and also the direct currents. As you know that you can rate the material in a mass. And today we will start to discuss about the inductance. It refers to L or inductor. So after we finish this chapter, I think that the students is know or they have a deep understanding about the three passive components in electronics or in electrical. It's like inductor and then resistor and also the capacitor. So for uh, inductance or for inductance passive component of inductor, the first we have to recall what is the Faraday's law in inductions. So how to create inductance or how to create a current using the magnetic field. Before we start to discuss about the capacitor, we start with the electric field. But for the inductor, as you know that inductor and capacitor can store charge, as I discussed before. But for the capacitor store or save the charge in electric field, and inductor store a charge in a magnetic field. So you can see from the picture that if we have the magnet like this ones, this is the south pole and north pole like this one, and then we have a wiring like this one, and then if we uh, put a magnet, a permanent magnet or in inductance or electromagnetic magnets through the wiring like this ones. So the current will appear it's like this one. If we connect the wiring to the ampermeter will notify that there is a current in the wire like this ones. So the current appears if there is a relative motion between the loop and the magnet. So if the magnet move from outside to inside the wire and then outside again, inside again like this one, it's like the motion between the loop, the wire loop, and also the magnet. So the current will be appeared in the wire, and then the faster motion produce a greater current. So if you want to get a greater current, you have to move a magnet faster. And then if moving the magnet north pole toward the loop, say that we have the clockwise current, and then moving north pole away, and then the current will be moved in counterclockwise current. So it's like this one. So if we move inside the wire, instead to wire like this one, so the current will go to the like the positive current, and then if we move out the magnet from the wire, and then the current will be a negative magnet like this one. So this is like yeah, like if you know that we have two current. The first is DC current, and then we have the AC current. And for DC current, the magnet of the DC current is stable or is similar. This is the current, current A ampere, and then this is the time. So for the DC current like this one, so uh, from beginning to the end, or from so there is no chance in the DC current. But for the AC current like this one, so if we have the AC current, so The magnet of AC current is like this one. This is the positive, this is negative, positive and negative, like this ones. So it's like if we make a movement, or um, we move the magnet to the wire like this one. So the current, the resulting current is the AC current, because this is the positive, negative, and positive, negatives, like this ones. So we can create a current by using the magnetic field through the wire. So the current produced in the loop is we call it in inducer current, like this one. And the work done per unit charge to produce the current is called induced EMF, or this one. So the notation of EMF is like this. And then the process of producing current and EMF is called inductions. So induction is the process to produce the current uh, by using uh, by using magnetic field. It's like this one. And then it's like this one. So the first, if we have um, the wiring like this one, this is the, like we have the A wiring, and this is the B wiring, like this ones. Okay. Um, it's like this one. If we have the wiring like this is the A wiring, and this is the B wiring, like this ones. So the ampermeter here will register the currents in the left-hand wire loop, or the A wire loop, uh, if the switch is close, if the switch is closed, like this one. And then if we switch is closed, switch off, like this one, so the ampermeter is there is no currents, because in here the current, or the magnetic field created by this wiring, this is the like circular path of wirings, will go from the first from the B to A. So it's like a transfer of current from B to A, so we can register the current in the ampermeter here. It's like you see that you have like antenna. So the antenna can deliver a data from one side to another side. um, why they can deliver the data? Because it's like they deliver a magnetic field from one side to another side, and another side of the antenna, or receiver antenna, can store, or can receive a signal, data signal, so we can produce a signal in the receiver. Or in another cases, like that wireless charger. So wireless charger is like this one. If we have the charger, and then we have the coil from transmitter coil, like this one. So this is the wireless charger. Wireless charger, and then another, we have the coil, and we have the like maybe a cell phone here. And then if we switch on the wireless charger here, and then the current will go to the coil, the transmitter coil. TX, this is transmitter coil. RX is receiver coil. And then the magnetic field of the coil transmitter, will move, or will transfer to receiver coil in the receiver. So for the wireless charger, they can transfer the current from transmitter to receiver, and then in the receiver they can receive the current, and then charge a cell phone in the receiver side. It's like this one. So this is the induction. And then this is the Faraday's law of inductions, and the magnitude of the EMF induced in a conducting loop is equal to the rate which the magnetic flux. So the magnetic flux is, it's like you remember, this is the we have magnetic field. Yeah. sorry, we have electric flux. This is the electric flux we discussed before, and today we know that this is the magnetic flux through the loop change with the time. So this is the EMF. EMF is minus d magnetic flux per dt. So this is the Faraday's law. And then if we have the coil, uh, if we have like a coil have some turns, so the EMF will change, depends on the turns of the coil, like this one. So EMF is equal to minus n the flux magnetic per dt, like this one, where the magnetic flux is integral of b dot dA. It's like you for the magnetic electric flux, integral of E dA, right? This is the flux, electric flux. Yeah. Okay, I jump from the step point one, and then what is the Lenz law? The Lenz law. This is we will discuss about opposition of the pole movement, and then opposition to the flux change. So, and if we have the magnet, and then the magnet's motion creates a magnetic dipole that opposes the motions, like this one. So if we have the magnetic motion in the loop, in the wire, like these ones, so they will create induction, yeah, inductions. And then uh, if we know that in the motions we have, if we have the action, there is a reactions, like this one. So we have the actions, and then we have the reactions. So it's like similar in induction. If we put a magnet in the wire, we create an induction, and then from the inner of the wire, they will create the opposite opposition of the inductions, like these ones. So we call it uh, a dipole moment. So the dipole moment is in opposite with the motion of the magnets. Okay, so it's like this one. If we put a magnetic field of B, like this ones. So this is the magnetic fields of B. It's like we put a magnet here, and then this is the South Pole and North Pole here. And then if we move the magnet through the wire like this one, so the B, the direction of B is to like this one. This is the below to the wire, and then they will create the induction, the magnetic induction of B in opposite direction with the B. So it means that if we increase the external fields B, so it will be induced the current. This is the current induced by this the magnet. Okay, so if we put a magnet in the wire, and then we create we put a B magnetic fields, so the wire will create a opposition magnetic. We call it B in, or induction, B induction. And then because of we create a B inside the wire, so the current will be generated, like this one. And then if we decrease the external field, it decrease, it means that if we put the if we move out the magnets, like this one, so it's like this one in north. So it's like we put, this is the wiring, and then we have the magnet, and then we like the motion of the magnet is like this one. So it's through the wire and then move out like this one. So it's mean that the external side, like this one. So this is the magnet, and then we go to the wire and then move out from the wiring, like this one. So it's mean that we decrease the B. So the decreasing of B So the B in will uh, will create from the wire in the same direction with the B, and then the current will in opposite direction. So the current generates in the wire is depend on the direction of the B in. It's like using the right hand. So this is the B, this is the direction of B in, and then and the forefinger is the direction of the current. uh, we we see in the A like this one. So if the B in is in like this one, so from to the above like this one, so the current generates in the counterclockwise like this one. And then if the B in the second in the B go to below the Y like this one, and then the current generates in the clockwise like this one. And then if we increase again, it means that the first we increase the B and then decrease the B, and then again we increase the B by put the magnet through the wire like this one, so the B increase again. And then if we increase the B, so B in opposite direction with the B, and then the current using the right hand like this one, so in the clockwise. And then if we decrease, it means that if we move out the magnet from the wire like this ones, so the B in will in the same direction with the B, so the current will go like this one. So I hope this is you understand about my explanation about the Lenz law. So Lenz law is how to generate the currents by using the magnet, and then the current is depends on the direction of the B in. So the current didn't don't isn't depend the current uh, not depend on the direction of the B, but the current depend on the direction of B in, like this one. See, so this is the Lenz law. And then if we have the wire like this one, so we can calculate the flux. So if we have the magnets like this one, so the cross like this one is mean that the direction of the B is go to the paper, or go to the paper like this one. So inside to the paper like this one. So we can check using the also the using the right hand like this ones. So this is the B, so this is the direction of the B, and then this is the direction of the current. So if using here, so this is the B and this is the current, and F2 will go to the upper level like this ones. So in second, if F1, so the current is go to above like this ones and be inside the paper, so the F like this ones. And then for F3, the current and the current B and the F3 has become this ones. So the magnetic flux is BA. Yeah. So in this case, the A is the area between the wiring and the magnetic field like this one. So this one. So this one the is A. This is the L. L is this one, the width, and X is the length, like this one. So A is L dot X. So the magnitude of the EMF, E is equal to d flux B per dt. So we change flux by BLX like this one. So d BLX per dt. So BL is constant, so we can move like this one, BL dx per dt, and dx per dt is v. V is the motion, is the velocity of the motion of the wire like this one. So this is the velocity. So EMF is BLF. And then how much the induced current in the wiring is I is equal to F per R. So F is EMF per R. So EMF is a BLF per R. And then thermal energy is P is equal to I quadrat dot R. So the P is, we substitute I by using this one, so we can get this one, BLF dot R quadrat dot R. So we can get like this one, this calculation to calculate the thermal energy. Okay, and then um, we will discuss about the eddy current. What is the eddy current? So if we put like a solid conduction plate out of the magnetic field. So if we have a magnetic field like this ones, and then we have the solid conducting plate like this ones. So if we pull a solid from the magnetic fields, so in the edge of the solid like this one, in the edge of the magnetic field, so it will be there is a eddy current loop, so it's like this one. So the typical loop of eddy current is like this ones, and then the conducting plate is allowed to swing like a pendulum about a pivot. So it will be enters like this one. So if we put a solid conducting plate around the magnetic field like this one, so they move like we have the pivot like this one, so they move inside of the magnetic field and outside of magnetic fields, so it will be also generate a eddy current in the edge of the magnetic field like this one. So this is the eddy currents. And then so the changing of magnetic field, it produces an electric field. So if we have the first, if we have the magnetic field like this one, this is the magnetic field. And then if the magnetic field is increased by using some, yeah, many ways to increase the magnetic fields, like we move the movement of the magnet will faster like this one, so the magnetic field also increase, so the constant induced current is appear like this one. So if we will get the EMF, and we have the currents like this ones, and then um, the induced electric field exists, it will be exist even the ring, the wires is removed from the magnetic fields. So in the electric field like this one, we get a point in the magnetic field. Why it will be creates the electric field? Because we have the EMF here, and then also there is the current here, so it will be create electric field. As you know that the if we have the charge, and the area around the charge is the electric field, so the charge is mean the current. So around a charge we have the electric field like this one. So we get if the charge of if the charge move in the electric field like this one, so we have the electric field line like this ones. And then we can check in this graphic that the electric field in the 1 and 2 is similar, but in 3 is not similar, because there is an area outside the electric fields, and also the electric field in 4 is 0, because there is no magnetic field in the area of 4. So from this figure, we can conclude that if we have the electric field, and there is the changing of the electric field, magnetic field, sorry, if there is a changing of the electric magnetic fields per time units, so we can create the electric fields. So this is the another Faraday's law. So the a closed integral of EDS is equal to minus d magnetic flux per dt. And then after we discussing about the eddy current and also about the induced electric field, we can create the electric field because of changing of the magnetic flux. We will now discuss about the inductor and inductance. A capacitor can produce the desired, can store a charge and can produce the desired electric fields. An inductor also can produce the magnetic field and can store a charge in a magnetic field. And the inductance of the inductor is L is equal to N magnetic flux per I. This is the magnetic flux, and this is the turns of the coil, and this is the current. Okay, and then the unit is 1 Henry is 1 Tesla meter quadrat per A. And then for any inductor, yeah, any inductor, because we got this one, yeah, and magnetic flux is equal to L dot I. And then recall that electric's Faraday's law, EMFL is equal to minus d and magnetic flux per dt. And then by combine this equation, we get that EL is equal to minus L dE per dt. So if the current in the coil is changed by varying the contact position of the variable resistor like this one. So if we have the variable resistance like this one, and then the current is changed, so the EMF will appear in the coil while the current is changed. So the key term of how to create the EMF here is how we can change the current. So it's like this one. So if we have this is the battery like this one, and then we have the resistor, and then we have the inductor like this one. But the current here, this is the current, is not changing. It's like a DC. So there is no EMF. EMF is equal to 0 here. But if we change the currents, so here we can create the EMF. This variable resistor can change the current. So we can create the EMF here. And then by using the RL circuits like this one, so we using the loop dot minus IR minus LdE per dt plus E is EMF here, or a battery is equal to 0. So LdE per dt plus Ri is equal to E. This is, and then we have the solution. I is equal to V per R dot 1 minus E minus RT per L, like this ones. So we can get this equation, and then if we change using the tau L is equal to L per R, so we can make a simplified equation like this ones. So we get two tau. One is for the capacitor is RC, and then for the inductor is L per R. So this is the time inductive time constant. And then what is the energy stored in magnetic fields? We can get this is the RL circuit. E is equal to LdE per dt plus IR. And then if we multiply it side by I, EI is equal to LIdE per dt plus I quadrat dot R. So the magnetic potential energy UB, we can get like this one. The UB per dt is equal to these equations. And then dt is we can remove, so the ub is equal to LI di. So we make integration like this one, so we can get that ub is equal to a half of Li quadrat. So this is the magnetic energy of the magnetic field. And then another is the last is mutual induction. So if we have two inductor like this one, so it is inductor 1, and then this is inductor 2. So the magnetic field produced in inductor 1 will induce to the inductor 2. It's like this ones. So if I1 here is we change the currents. So there is the induction. So they will induce to the magnetic field. So we can produce the magnetic field here, like B1, and because of B2 is near of B1, so the magnetic field of B1 will go to the B2. So it means that this is the mutual inductance. So the mutual inductance of M21 of coil 2, so M21 is coil 2 is respect to coil 1 is defined by M21 is equal to N2 flux magnetic flux 21 per I1. Here for the simplify is if we how to calculate the M21 is because M21 or mutual inductance of inductor 2 is because of inductor 1, and inductor 1 we change the current, so the mutual inductance of M21 is depends on I1. So it's like this one, and then uh, so we can get that uh, M21 the E1 per dt is equal to N2 the flux magnetic flux per dt. So on the right side is equation is according to Faraday's law. So we can get that the EMF appearing in coil 2 due to a changing current in coil 1 is equal to E2 is equal to minus M21 dE1 per dt. Is also similar if we put or if we make another way, like we change the current in inductor 2, and then it will be create the magnetic flux, a magnetic flux in B2 like this one. So it will be induced to B1, so we can calculate the M12, and M12 is equal to M21, and then we can measure the E1 is equal to minus M12 dE2 per dt. So M21 is equal to M12 is equal to M. So this is the mutual inductance. So the mutual inductance is if we have the inductor, two inductor in the position of two inductor is near, and then if we change the current in one inductor, it will be induced the inductor, and then it will be create a magnetic flux in one inductor, and then it will be induced to another inductor. It's like this one. This is we change the current in coil 1 and will be induced to coil 2. We change current in coil 2 and will be induced to coil 1 like this one. So the induction of inductor 1 to inductor 2 is we call it mutual induction. So it's like this one. And then we have the exercise like this one. In the circuit, R1 is 20 kilo ohm, R2 is 20 ohm, L is 50 millihenry, E is equal to 40 volts. Switch S has been open for a long time. When it is closed at time t is equal to 0. So just after the switch is closed, what are the currents through the battery? And then number B is the rate of the watts per dt, and t is equal to 3 microseconds. And then what is C? I bet. What is the I battery? And D is the E bet per dt for a long time later. And what is I bet? E bet and F the E bet per dt in the long time. So how to solve this equation? The first, uh, the inductor is series to the battery, and then a switch close t is equal to 0. So the currents 0 in the inductor. So in the initial conduction, because there is no changing of the current, and then there is no explanation about what is the current uh, before the switch is closed. So the t is equal to 0. So the current through the battery is also the 0. So if we have no current anywhere in the circuit, if the t is equal to 0, so the loop requires that EMF of the inductor will be cancelled of the battery. Yeah, so because of there is no T is equal to 0, the switch is on, and then so the EMF we create if the switch is on like this one, so EMF will create here in inductor. So it will be cancelled the battery voltage. So the EL is equal to 4T. So the EBAT per DT is equal to EL per L. So it's equal to 40 per 0.05 Henry. So 8 multiplied by 10.2 ampere per second. And then number C is it at time is 3 microseconds. What is the IBET and the EBET per DT? So the first we have to check the tau L. The tau L is equal to L per R, and then in this circuit there is 2R here, so we have to make equivalent circuit of R1 is parallel to R2, so we can get these ones parallel of 20 kilo ohm, so we can get R is 10 kilo ohm. So we can calculate the tau L. Tau L is L per R. So L is 50 millihenry per 10 kilo ohm. So we can get 5 10.96 seconds. So we apply to this equivalent this formula here. Yeah, this we can replace by this formula. So we can get that E bar is I bet is A per R 1 minus E minus 3 per 5 because the tau per T per tau L is 3 per 5. So we can get I bet is 1.8 10 point minus 3 ampere. And then the rates of change of the currents by using the figure like this one. So we can get the loop like this one, so we can get that E minus E bar. So so we can get I figure it out, like I draw again. This is the circuit before, and this is the R parallel of R1 and R2. So E, this is the current is I bet, and then this is the EL. EL is the EMF of the inductor. So we make a loop. E minus I bet E bet R minus EL is equal to 0. So using a value from from C here, we get that EL is equal to 22 volt. Okay, so we can get the EBAT per DT is equal to AL per L is 22 volt per 0.05. So we can get 4.410 quadrat ampere per seconds, like this one. And then as the T is equal to unlimited, the circuit reach steady state conditions, so that the EBAT per dt is equal to 0 and EL is equal to 0. And then the same loop, we can get like this ones. So we can get that EBAT is 40 per 10 kilo ohm. So we can get 4 multiplied by 10 by minus 3 ampere. So for the rates of the EBAT per dt, because the circuit reach steady state conditions, the EBAT per dt is equal to 0. So yeah, please repeat again for this explanation of the questions. So I think this is end of the electromagnetic induction and inductor. Okay, good afternoon. See you next time. Assalamualaikum warahmatullahi wabarakatuh.